Welcome to lecture number 14 of the course Introduction to Data Science. This is the second lecture devoted to process mining. In the first lecture we gave an overview of the field of process mining and focused on process discovery, which is an example of unsupervised learning. In this lecture we're going to focus on process mining techniques that are supervised, so where we are aiming at a particular goal, like for example understanding why there is a bottleneck, why there is a deviation, and also detecting such deviations and bottlenecks. So process mining is one of the core topics of the chair Process and Data Science. In this, let's say, IDS course, we only have 2 lectures devoted to that, but people that would like to dive deeper, I would highly recommend to take both the Business Process Intelligence course, the BPI course, and also take the Advanced Process Mining course. And there are also several seminars and practica that you can take into this area. Okay, let's look at the menu of what we will talk about today. I will start with a short summary of the previous lecture so that you can position the things that we talk about in the bigger spectrum. Then I will stress that if you do process mining, that is typically aimed at 2 use cases. That is improving performance, for example, reducing flow times, reducing waiting times, ensuring that processes have the right outcomes, and compliance. So often you have to deal with regulations and you want things to happen in a certain way. And what process mining often exposes is that many of the real behaviors are very different. And using process mining, specifically conformance checking, you can detect such things. So the 2 supervised learning techniques that we will talk about are conformance checking and, let's say, generating, let's say, standard machine learning problems on top of process mining techniques. I will be more extensive on the conformance checking part. I will be more superficial on the supervised learning part, so generating these supervised learning problems. However, given what I have told you last lecture, what I tell you about conformance checking and all the data science techniques that you have already seen, it should be relatively easy for you to make the connection. At the end, I elaborate a bit about tooling and let's say also what kind of role our group and the RWTH is playing in this bigger space. So the material is again coming from the book on process mining. On this slide I'm highlighting the chapters. Also in the last lecture I gave a pointer to the Coursera process mining course, which has already been taken by over 130,000 people. And in this course you can look at things in much more detail. The content is somehow similar than the BPI course, although the BPI course is going deeper. Okay, but let's start with a short recap of what we talked about in the last lecture. So process mining is the connection between process science and data science. You could also say it's the part of data science that is focusing on end-to-end processes. We are concerned with things like performance and compliance, as we will see today. And we are taking very general event data as input. So this data could come from machines, they could come from like a car factory, production processes. They can also come from administrative environments. They can also come from hospitals, from social media, etc., etc. We talked about event data extensively before. A typical starting use case for organizations to start using process mining is that they apply it to let's say their let's say core administrative processes, for example their sales and their procurement processes. So SAP, just as an example, is loaded with event data. I've explained this diagram before. It is basically showing that a process consists of cases. A case is composed of events. Events can have different attributes, timestamps, cost, resource information. We may also have start and complete activities, so that we can see an event highlighting that an activity instance has started, and another event that is indicating that the activity instance has ended. Just like in the last lecture, we simplify it incredibly, that we can talk about the core process mining techniques, and we rewrite such event data into a multi-set of traces, where every trace is a sequence of activities. So we are basically just using timestamps for ordering, and we are abstracting from, for example, from resource information. I assume that everybody is familiar with the notation of multisets, and that you can see, for example, in this example, we have a log L2 that has a bunch of cases, and there are 3 cases that are following the pattern or the process variant, where we first execute activity A, then activity B, then activity C, and complete with activity D, etc. This should be nothing new. And if we do discovery, we take such data, and based on such data, we automatically learn process models. And this often leads to very surprising phenomena. It is often described when people see in their organization process mining for the first time. They respond like people that are seeing snow for the first time. So people still find it amazing that you can do these things based on the data that they always had but never used in a proper way. If you look at highways in the data, in the event data, then you can construct models like this. If you lower the threshold and you allow also for showing, let's say, paths with a lower frequency, we see this. And we can, instead of showing frequencies, we can also show times. So this is an example of Celonis. This is a simply directly follows graph. There are, let's say, over 35 commercial tools that can do these types of things. And also in the open source domain, so for example in PROM, all these functionalities already existed, let's say 15 to 20 years ago. This is not difficult, but it is very, very useful. This is in Celonis. This is another tool, Disco, just to show you that in many of these tools you can let's say show these directly follows graphs that basically show how cases are flowing through the process. And you can play with color and thickness. So for example here you can see that on average almost 12 days pass between placing an order and pay if people start by payment activity before they get the invoice. We looked at, let's say, various discovery techniques. I explained to you that if you're using Petri nets, process discovery can be described as the process of simply finding the Petri net places. That's the bottom-up approach. And there are also top-down approaches, like, for example, the inductive mining approach. And this is the approach that in the last lecture I explained in more detail. So we learn a process tree, but that process tree can be converted to any notation that people would like to see. Petri nets, BPMN, UML activity diagrams, UML state charts, etc. So that was discovery. The next question is, okay, this is all very spectacular, but why do organizations do this? Why is this useful? Well, why is this relevant? Well, process mining is the connection between process modeling, looking at processes, how you can improve them. And so it says here process models, but you could also talk about process management in general. And on the other side, you have the event data as they are in systems. Organizations know that they have this type of data, but can do nothing without it. And process mining is let's say, connecting these two perspectives. These activities often aim at performance problems, and that's one typical use case. And here I'm overlaying, let's say, the statement process mining is used for performance analysis with, let's say, the 4 types of questions that people ask in the context of a data science project that I introduced in my first lecture. And so, for example, the first step is reporting. So, given process mining, we would like to understand where are the real bottlenecks and determine that objectively. If we have determined where the bottlenecks are, we would like to generate a diagnosis explaining us what do these have bottlenecks, what is causing these bottlenecks, what do cases that get delayed, what do they have in common. After we understand that properly, we can use prediction. And so we based on the things that we have learned on the data, for running cases, we can predict what is going to happen to these cases. And if we can do predictions, then we can automatically also generate recommendations. Because if we can make predictions, we can basically act as if we make a certain decision, then look at the prediction after making the decision, without already making the decision, and then we can, let's say, basically have a recommendation based on the best alternative. So this is when we look at performance problems like a bottleneck or cases that get delayed. And here are some let's say typical examples just to show the spectrum. Process mining is, for example, used to analyze, let's say, baggage handling at many of the airports. It has been applied to the analysis of bags at Heathrow. So questions that you see here is, okay, why do bags miss a plane? What is causing delays? Why is at some days the capacity of the airport not sufficient, although it should be? Airports are a bit like systems that sometimes have the flu and for unclear reasons are not able to deliver the performance that they should. So that's an application. Then you can look at hospitals. For example, a hospital has a kind of service level agreement. They say, okay, if a doctor needs a certain treatment, then we guarantee that we can start this treatment in, I don't know, 4 weeks. If that is not the case, can we detect that we are not meeting the service level agreements, and can we explain why? These types of questions. We can look, as I said, in the area of logistics and production, of course. If you look at companies like Amazon, of course, they have incredible amounts of data and can learn a lot about how to handle these things. So what probably many of you know is that Amazon is also doing many things based on predictions. So they already start to move goods before the customer order is actually there, because based on the data that they have, they can predict these types of things. So these are environments where you can use process mining. It has also become a standard practice for, let's say consultancy firms to provide process mining services. So this is with the performance view. We can also tell exactly the same story with the compliance view. So now we are not so much interested in things like bottlenecks. We are much more interested in, okay, we know how we want the process to behave. Why doesn't it behave in this way? So now you should think about things like for example, fraud, or so fraud sounds very serious, but there are also, let's say, lots of, let's say, regulations that exist within organizations that people are supposed to follow, that if we look in practice are not always followed. I've been involved in many projects where people would say, okay, it is very important that this and this and this happens in this and this order. And then you would look at the data and you could sometimes find that in more than half of the cases, the actual process is violating these important rules that were described. So compliance problems come into play when we have a normative description of what should happen, and again we can answer the 4 questions. So we can detect these problems, we can explain these problems, we can predict whether they are going to happen, and we can also recommend countermeasures to avoid that there is going to be a compliance problem. And again, I could walk through the same for use cases. So now we are not in a discovery mode, but we are in a mode where we have a normative description of what should happen, and then we can look at whether we find certain deviations. And so, for example, in an airport, it's very important that nobody is messing with the bags from the moment it is checked in to the moment that it goes to the plane. So there are certain behaviors which are, let's say, physically impossible. So for example, one bag overtaking another bag, or one bag that is suddenly missing and is reinserted later. Using conformance checking, you can detect such things that are not supposed to happen, which seem to be impossible but still happen anyway. I could tell the same story about medical guidelines. So when doctors are treating patients, they are supposed to follow certain guidelines. They deviate from that, often with very good reasons, but you can use process mining to diagnose such deviations. The same with let's say logistic, payment, procurement processes. And so, for example, if you could see that goods get shipped without having a payment already, so you could zoom in on these cases and try to see what they have in common. And of course, for consultancy firms, fraud detection, auditing are of course, let's say, the main processes that they do that are becoming much more analytical in nature, also because of, let's say, the uptake of process mining techniques. Okay, so this was just to set the scene again, that we can position the things that I will talk about in the remainder in this, let's say, bigger framework. So the first technique is conformance checking, and it is different from discovery in the sense that we have a model and we would like to see, okay, does reality now behave as we have described it in that model? So if you look at the diagram that I showed before, the world is generating events that are stored in information systems, in databases. We extract event logs. We also have models that have been discovered or that have been made by hand, and we would like to check, does reality behave as the model says that it should behave. And then you often find things like this. So in this picture, we see a gate here. Yeah, and you can think of this as a process model. It is describing how things should happen, and this is there with a certain reason. I don't know, to avoid fraud, or to avoid that customers get questions that they should not have. So this is there with a good reason. Sometimes information systems are, let's say, trying to enforce such, let's say, business rules, compliance rules, but in reality this is happening. So here we see a difference between the model and the event log. And this model can be a model that just exists on paper. It can also be a model where the organization is trying to partially enforce that through the information systems that they provide. But still, people may deviate. It's the same example as in the airport. If bags are on a conveyor belt, then you expect that that they leave the bags in first out order. If the order has somehow changed, one would say, okay, that is not possible. But if it happens, then it means that somebody took the bag off the conveyor belt and reinserted it later. And you can think of these behaviors that you think cannot happen, that happen all the time. And this is the field of conformance checking, and that is why it is relevant. To become more technical, I switch to, let's say, ABC examples, because that is the only way to explain, let's say, also the more conceptual or technical side of things. We now have a process model, and we assume that we have an event log. And remember, in the setting that we are using, our event logs are a multi-set of traces, and every trace is a sequence of activities. So this A, B, E, G, you should think of this as a sequence of activities, and it describes what is happening to a particular case that is flowing through this process. On the other hand, we have a process model. I hope also after the previous lecture that you're now already a bit used to let's say, such notations. I'm also, let's say, partly assuming that let's say, in the bachelor courses that you had, that you already had courses that deal with, let's say, process models. But just to refresh this a bit, this process always starts with A. So we have an initial marking, as we call it, with the token in place start. It always starts by executing register request. Then there are two sub-processes executed concurrently. And so these two branches can be executed in any order. These activities may also run, let's say, concurrently at the same time. Here there is a choice between B or C. So if there is a token here, we can go like this, or we can go like this. E can only be executed after B or C has happened and D has happened. It could be that D is finished before B or C, but it could also be that B or C is finished before D. But both need to have finished before I can execute E. After I execute E, there are three possibilities. I pay, I send a rejection, or I execute this reinitiate request activity called F. That basically brings the system or the process back into the state after that we were also in after executing A. So now we have a model, we have a trace, and now we can simply replay this trace that we see here on top of the model. So we execute A first, we consume the input token and produce two output tokens. Now the log says, and the trace in the log that we are examining says we should do B. That is indeed possible. So we execute B, and we are at this stage. Now in the next step, the log says, or the trace that we are inspecting says, okay, the next activity is activity E, decide. But if you look at the process model, you know that that is not possible. And so when we are replaying this, we can indicate that there is a problem, but E happened in reality. So we need to deal with this in some way. So what we do is we add the so-called missing token. And so M stands for missing token. We say, okay, we have a missing token at this stage, and then simply execute E as if the token was already there. Finally, we do G. So we consume one token and produce one token. What we see is that the token is remaining here. So we have a remaining token, we have a missing token. And if you, let's say, replay this complete game, I will be more precise about this later, then we can count produced, consumed, missing and remaining tokens. And it is of course clear that if we do not have any missing and we do not have any remaining tokens, it's perfect. But the more missing and the more remaining tokens we have, the more problematic the particular trace is. And we can capture this into a so-called fitness number. You can also think of this as a kind of recall measure, although there are also differences. We have this formula that is basically generating a number between 0 and 1, where 1 means that there is perfect fitness, and we did not encounter any problems, and 0 means it's the worst possible situation. So for example, if m is equal to 0, we can write a 0 here and we can write a 0 here. Then we have half times 1 plus half times 1 is 1. So if there are no missing and no remaining tokens, we get a perfect fitness equal to 1. If on the other hand, all the tokens that we consumed were missing in the first place, and all the tokens that we produced while replaying were never actually used, were all remaining, then we have the worst possible situation. Then you have 1 minus 1 plus 1/2 times 1 minus, let's say this factor is also 1, so this becomes 0, this becomes 0, and the overall fitness is also 0. And so these are the two extremes. If we fill out the values from our scenario, we indicate the missing and the consumed tokens, the remaining and the produced tokens, and if we fill out the formula, we have a fitness of 0.833. So this is just a definition that quantifies this fitness notion, but what is of course much more interesting are the diagnostics that you can create in this process, is highlighting the parts on the process where there are the biggest problems. On the other hand, whenever we identify a problem, we can drill down and find the cases that had this particular compliance issue. So we already now get more technical. So if we look at a place, then there are two ways that the place gets a token. A place can get a token because a token is produced for it, and an activity executes and it puts a token in each of its output places, so that is this P. Then there is consumption, so an activity called PetriNet, called transition in PetriNet terms, is consuming a token because it fires from one token from each of its input places. This is the normal behavior, production and consumption by PetriNet transitions. If there is a problem, then the problem is that like we would like to consume something, but the token is not there, and then we need to add missing tokens. So these tokens were not produced, but we had to add them. And we have R, and R are the tokens that remain after we have completed the entire trace. So these are the things that were produced, but that were never actually consumed. I hope that you understand this, that at the beginning such a place is empty, at the end the place should also be empty, and you should understand that P plus M should be equal to C plus R at the very end. So while running, the number of tokens is equal to P plus M minus C. So what was produced, what was added because it was missing, minus what was consumed, is the number of tokens. And at the end, this number should be 0. So we remove, let's say, all the tokens that are still there at the very end. And that defines R. So based on these observations, you can deduce several invariants. The bottom one I already explained. So if we look at one PetriNet place, then we know that at the very end, the number of remaining tokens is equal to P plus M minus C. So this holds for every place, but we can also sum this up over the entire process model that may have more, let's say, PetriNet places. So this is what we have at the end. While replaying, we also have, let's say, this invariant, so that always holds, that P plus M is at least C, and C is at least M. You should note that we never add a missing token unless it needs to be consumed, right? So the number of missing tokens can never be bigger than the number of consumed tokens, right? Because there has to be something missing. Similarly, you can derive that P plus M should be bigger than C. Places cannot go negative. So these are some invariants that are there. Then there is a special step at the beginning. So what I said, all the places start empty and end empty. If something is remaining, we remove them and update the R counter. There is a special step at the beginning because the input place is also empty. The environment starts by putting a token on the input place. And at the end, the environment ends by consuming a token from the sync place. And there you should note that also if there is no token in the end place, so if this place is empty, we still consume something. So that means that if at the enter of the trace this place is empty, we first need to add one missing token in such a way that we can do the consumption action. And so at the beginning we produce a token for the place where it all starts, and at the end we remove a token from the end place, and if there is no token there, we have to add a missing token there to detect that we did not reach the end properly. Now I've explained you everything, and I can just run through, let's say, a large number of examples to give you a feeling for how this works. So here I'm looking at a trace A, C, D, E, H, and for the people that can read battery nets, they immediately see that this trace fits. So this will be a bit of a boring example, but it makes it will help you to get used to the counters and the way that we replay things. So it starts by the environment putting a token on the input place. So I've incremented the P counter because this is always what happens in the beginning, and there is a token here. Then the log says that we should execute an A. This is what we do. If we execute A, we consume one token and we produce two tokens. So pay attention to the P and the C counter. If I now execute A, these two counters get updated, so P becomes 3 and C becomes 1, because we consumed the token from place start. So now we have updated the counters, and we look at the next step in the trace. So now we should execute C. That means that we consume and produce a token. So again, take a look at this at these two counters, the P and the C counter. They will be incremented both with 1. That's what you see here. So now we have 4 produced tokens and 2 consumed tokens. If we take the difference from 4 to 2, we see that indeed there are 2 tokens in the network. That's how you can check this. Next, the log says that we should do D, and again we update the counters. Then we should do E. Perhaps I should spend a bit more time on this step. So now we execute E, this transition. So we are consuming 2 tokens and we are producing just 1 token. So we have 5 and 3. We consume 2 tokens, so this counter will go to 5, and we produce 1 token, so this counter should go to 6, and that is indeed the case. Yes, here you see the resulting numbers. Then we do H, again we produce and consume 1 token. Here are the updated numbers. And finally, very important, at the very end, the environment is going to take a token from the end place, the sync place. In this case there is a token, but it would also do that if there was no token, and then we would also have to add a missing token there, in such a way that the environment can consume it. But that is not the case. Now we simply update C with 1, and now we have reached the very end. So P is equal to 7, C is equal to 7, M and R are equal to 0. We go back to our formula, we fill out the numbers, and surprise, surprise, the fitness is perfect, it's 1. And this is what I explained before. If there are no missing and no remaining tokens, this is always the case. So that was a bit boring because there was no problem. Let us now take a look at this trace, where we do A, D, C, E, H. I think this was something that was possible in the previous model, but I've made the model more sequential. So I'm doing now first these checks before I'm doing, I'm first doing one of these two checks before I'm doing D. So I took the previous model and I made it more sequential. So now we can replay the log on this model. So we start, the environment puts a token in there, and we start by executing A, which is consuming a token. So far everything is the same as before. Note that A consumed 1 token and produced 1 token. And again we can take the difference and we see there is indeed just 1 token in the net. In the previous model A would produce 2 tokens, but here just 1. So everything is fine, but now it gets interesting because we want to execute D. D has place P2 as input place, but that place is empty. So we know what we need to do. We need to add a missing token here in this place P2, and then we can execute D and let's say consume 1 token and produce 1 token. So now we are updating 3 counters. We are updating the P counter with 1, the C counter with 1, but also the M for missing tokens counter by 1. And this is what has happened here. And so we have updated these 3 counters. After doing D, we now see that C is being executed, and this is business as usual. We consume and produce 1 token. That's what you see here. So we have now executed the trace until this point. Now we need to execute E, and that is possible. We update the P and C counters again by 1 to reflect this execution. Finally, the log says we need to do an H, and if we do an H, we again produce and consume 1 token. So we update our P and C counters. Now the environment takes a token from the end place. It is also there. So if it does that, we are only updating the C counter and the C counter by 1. So this is what we get. So at the very end, all the places are supposed to be empty, and we have this rule that all the tokens that remain become remaining tokens, and we consider that to be bad, that something is left behind. We update the remaining token counter by 1, and we have these numbers. I can fill out, so this was our result, we can fill that out in the formula, and this is what we get. I think it should be fairly straightforward how this works. So this is showing the formula for, let's say, a whole log. Just to explain what we have been doing so far, we are applying this fitness value on a particular trace, a sequence of activities corresponding to a case. But the same case can appear multiple times. The same trace can appear multiple times if there are multiple cases having exactly the same trace. And of course there can be cases that have different traces. So we have a multi-set of traces, and over this multi-set of traces we need to compute fitness. And this formula looks scary, but it is actually not scary at all, because we are basically summing all the missing tokens over all the different variants that we see in the log. And of course, if there are multiple cases having exactly the same, let's say, sequence, we should count that multiple times. And so note that L is a multiset. L sigma is indicating how often sigma appears in multiset L, and the same for all the other ones. And so as I said, this looks scary, but we are just, let's say, summing over all the different cases. So this is the total number of missing tokens for the entire log after replaying not a single trace but the whole log, and the same for consumed, remaining and produced tokens. So this should be fairly straightforward. To do this by hand is of course very tedious, but of course for a computer this is not a problem at all. So here I show an artificial log, but it's a log that is already a bit more complicated. So we see all the traces, and I'm not using the mathematical notation for a multiset, but I'm showing a table, just to make things readable. So the trace sequence of activities A, C, D, E, H happened 455 times. If we look at the traces here at the bottom, which seem to correspond to loops, they are happening just once or 2 times. Now we can look at the corresponding possible models. So these models could have been discovered, these models could have been made by people as a normative model, and now we can compute the fitness. And now think about the use cases that I've been talking about before. I have a log, I have a process model how I want things to happen, and now I can actually attach a number to the level of compliance. And so how well reality is following these models. And you can, I hope that you understand that such applications are omnipresent. Of course, my examples are a bit, let's say, abstract with A, B, C, D, but this is the only way that I can explain this in a meaningful way. So in the previous slide, I was showing the fitness values for log model combinations. But of course, what is much more valuable than having a number, like 0.95, it's much more valuable to get diagnostics where the problem is. So here we see if we replay the original log on this model, then we see that there is a problem in P2, and you can see that there are over 400 missing tokens indicated by the minus, and there are over 400 remaining tokens indicating by the plus symbol. So the problem is here, and yeah, this is showing, because there is plus and minus, that there is an ordering problem, and this is caused by the fact that in the process, as we can see it in the data, D is concurrent to B and C, and here it is forced to be sequential, and the diagnostics show that exactly. Here is another example. I'm not going to explain that in detail. I just showed you, given a log and a model, we get a value, and next to the value we also get diagnostics. So for example, this minus 146 is indicating that D happened in reality, but according to the model this was not possible anymore. The plus values that you see here, they are indicating that something should have happened, but it did not happen. And because tokens were remaining at the end. So again, minus means while replay we had to inject missing tokens. Plus means at the end tokens were remaining. So minus means that something is happening in our data, but it was not possible according to the model. Plus means tokens are remaining. That means that something should have happened that did not happen while executing the trace. That's how you can intuitively understand this. Now I have a large a set of examples, and you will also play a bit with this in the instruction. I should add, when I go into these details, there is also an overlap, of course, with the business process intelligence course, where you see also such things. But the business process intelligence course goes much deeper into these topics. But just like possible overlaps with previous courses when we were talking about regression and decision trees, of course we see a similar phenomenon here. But I guess there are also many of you that in the end will not, let's say, take the BPI course, and still this is important. So I have here, I'm showing a log in tabular format, as I said before. So we have traces, and this is the frequency. So 10 cases are following the trace A, B, C, D. And now the simple question is, I have a model, I have a log, compute the fitness. So now please stop the video and try to do this yourself. You have been given a log, you have been given a model. I explained to you, let's say, how token-based replay works. So you should be able to compute fitness, and you should also be able to show the diagnostics in this diagram, just as I showed it before. Well, as indicated, this may take some time. I'm not going to do it in this lecture showing, let's say, every trace, but I just give, let's say, an example trace, and later I gave the numbers for each of the traces. So suppose that we focus on ACD, that is happening only once, indicated here in red, and I just play the game. So the environment produces a token on the input place. Then we execute A. So I add the consumed and two produced tokens. Now we do the C. I add the consumed and produced token. Now I do a D, and I have a problem because the data says that after C I should do D, but according to the marking of the PetriNet, this is not possible. But we still force D to happen, so we add the missing token. And now we can consume two tokens and produce one token. At the end, the environment will need to consume a token from the final place. It is also there, so that's good. And now we look at all the places where they are empty. But you can see here there was a produced token in P1, but nothing was consumed. So we see that there is a remaining token here. And now we can look at the numbers. We have 5 produced, 5 consumed, 1 missing, and 1 remaining token. And just count all the let's say P annotations, C annotations, etc. So for this single trace, we know that these are the numbers, and these are, let's say, part in this bigger formula. So here I'm showing this as in a spreadsheet form. So what you see here at the beginning are the let's say is the input, so the traces and the frequency, so a multi-set of activity sequences. Then this part is showing the diagnostics for a single trace, and then we multiply these numbers with the frequency of that particular trace. And then we add up all the produced, remaining, consumed and missing tokens, and then we fill this out in this formula. So this part, so the total number of missing tokens is equal to 7, etc. So this was the trace that we looked at. So the numbers 5, 1, 5, 1 you could also see on the previous slide. This trace is happening only once. So if we look overall on all the cases that follow this pattern ACD, the values are exactly the same. If we take a look at the first one, which is perfectly fitting, you can see that for one trace we have 6 produced and 6 consumed tokens. Because we have 10 traces, we multiply that by 10 and we get 60, 0, 60, 0. All very easy, I think. Then you add up all the different columns. Then you have the total number of produced, remaining, consumed and missing tokens. You fill it out in this formula and you get this fitness value. So this is simply filling out the values, and this is what we get. If we load this into process mining tools, here you see, let's say, a screenshot of the previous version of PROM, which is showing that very nicely. So what we see is the fitness value that we just computed. We can see, let's say, where tokens were missing and remaining per place. So this is these provide very valuable diagnostics. What is also doing it is indicating what are the cases that are now fitting. That is, let's say, 58% of all the cases are fitting. And we can now either select the ones that are, let's say, compliant or the ones that are not compliant and use them for further process mining analysis. And I hope that you can see that this is the way to generate supervised problems. If you can split cases into fitting and non-fitting, then you can turn this into a supervised learning problem to predict when cases are going to deviate or not. This is another log. It's a bit of an odd log, but it is intended that you also see situations that I did not show before. So again, stop the video, make this by hand, and that will tell you whether you really understand what I've been talking about so far. So use pen and paper and annotate the Petri net with produced, missing, consumed and remaining tokens. So if I do that, again, the environment starts by putting a token in the initial place. So we have one produced action. Then E is the activity that is happening. So we need to do E. E's input places are empty. We need to add a missing token to them in such a way that we can do E. Then E happens, consumes 2 tokens, produces 2 tokens, and then the trace is already done. But we had this rule that at the end the environment should take a token from place end. That's the reason why I'm showing you this example. That's a scenario that we did not see so far. So we need to add a missing token here, and only after adding the missing token we can really come to an end. We have reached the end of the trace. We have ensured that we consumed the token from the final place, and now we can look what are the tokens that are remaining, and there are 3 tokens remaining, and you can see that even the token on the input place is remaining because A never happened. So now we have the whole formula, and we see that P, C, M and R are let's say all equal to 3. And if I fill this out in the formula, then of course this leads to a fitness of 0. And now you can see, let's say, what the worst case scenario is. The worst case scenario is that, and you can see that very nicely in this diagram, all the produced tokens were remaining. So everything that we produced was never actually consumed. They were all remaining. And all the consumed tokens, so all the tokens we had to consume, 2 here and 1 here, they were always consumed in a situation where there was no token, so all of the consumed tokens were also missing. And this leads to the worst case scenario where the fitness is equal to 0. This is another example. As I said, I'm going to rush through this because these are things where you should stop the video, make it yourself, and then simply look at the solution. And then you can already practice for things that you will also see later at the instruction. And it will also make you better understand the things that I'm talking about. So again, we have the same question. We have a log, model, what are now the deviations, and what is the overall fitness. So again, I can create a table. I can look at a particular trace. So for example, ACE is happening 5 times. If I replay ACE on this log, then you see that there is a problem because this place is indicating that A should be followed by D eventually, and B should be followed by E. Whereas this trace is following this path, it's first doing A, then C, that is still all okay, but then at the end there is no D, there is an E instead. So if I do the replay, this is what I get, and we can see the problem, right? We can see that after doing A token was produced, but D never happened, so there is a remaining token here. E was happening, but E happened without B happening before, so we also, let's say, have a missing token here. And so again, the missing and remaining tokens are showing exactly where the compliance problems are. This trace is happening 5 times. So we multiply the numbers here times 5, and then this is what we get. And we can do that for all traces, and then sum up the things, and then we get the expression. So we add up all the 4 columns, and then we fill this out in the formula, and this is the fitness value that we get based on this. And here are the diagnostics. And what you should notice that PROM reports exactly the same number as I just computed by hand. But PROM is also showing, let's say, detailed diagnostics in the process model itself. So we see that, for example, this activity happened in reality once while there was no token here. And at the end of executing all the cases, 3 tokens were remaining here. Right, so this should be straightforward now. Here's another example. Again, we have a trace and we have the corresponding frequency. Stop the video, try to do this yourself, that you fully understand. And these are the diagnostics that are generated for this. And so this should become fairly obvious for you now how this works. For the example that I just showed you, I'm showing that also the tool is reporting a fitness, and just that you can check what you're doing, you can see again the diagnostics. So we see that there is a -10 here, so these two activities together happened 10 times in reality, while according to the model they could not happen yet. In all the examples, so for example, if I go back, in all of the examples that we have seen so far, P is equal to C and R is equal to M. And of course, an interesting question is this always the case? In the beginning, I showed you some invariance, for example, that the number of produced and missing tokens is equal to the number of consumed and remaining tokens at the very end, as expressed by so how we compute the remaining tokens. Just move C to the other side and we see that C plus R is equal to P plus M. But this does not say that C should be equal to P and R should be able to M. Question is this always like that? Is that another invariant that I forgot to tell you about? And the answer is no. And it's actually purely by coincidence in my examples that these numbers were always the same. If I take a look at this model and this trace, then I can replay it. I can fill out the numbers, and you can see that this is a scenario where P and C are not equal and M and R are also not equal. Right? And this may seem artificial because one could argue, okay, I don't need to have 2 places here, but I could extend this and there could be instead of P1, there could be a small, let's say a small workflow. Instead of P2, there could be a smaller workflow and we would still have this issue. So they don't need to be the same. As is shown here, this is the fitness value for this, let's say, log consisting of just a single event. So this replay approach, let's say, is very, let's say, easy to understand. It's very direct. It gives you also diagnostics where there are problems. However, it is making a set of assumptions that I've not mentioned very explicitly. So for example, we assume that there cannot be two transitions in the Petri net that refer to the same activity. It cannot be that the same activity is happening in the beginning and the same activity is happening at the end. We also do not allow, this is a bit more technical, for so-called silent transitions. So for example, if we are skipping over an activity, then we cannot see that. So we have a so-called invisible transitions. So there are lots of, let's say things that I did not talk about. I just explained you the essence of things, but implementations are dealing with this in several ways. So token-based replay is supported in PROM. Also in P and for Pi you can do, let's say, token-based replay with some optimizations. But also, like in systems like Celonis, for performance reasons they are doing, let's say, token-based replay, because that is the fastest way to do conformance checking at this point in time. But if you have multiple activities with the same label and they are both enabled, how do you pick one? And there, let's say, heuristics come in. Also conformance, if we have a net with a loop and many things are not fitting and we are going to the loop multiple times, then at some point in time there will be tokens everywhere and you never need to have a missing token, even though nothing really fits. So sometimes conformance values are too high, they are misleadingly high, although the relationship between the log and the model is very weak. So there are all these limitations, and yeah, to talk more about that would go too far in this lecture, but there are, let's say, more sophisticated techniques that do not have these types of problems. And so at this point in time, specifically in the academic world, the notion of alignment is the, let's say, central topic to do this. So the basic idea of alignments is to make it more objective, and you basically are solving an optimization problem given a path that we see in the data. We try to find the path in the model that is closest to the path that we have seen in the data. Of course, it says here the closest path. I think intuitively you can see that there can be multiple paths that have that, let's say, property. So we can also return all if we want. So alignments are showing exactly where the deviations take place. Alignments are also, and that is to use for the things that we've mentioned, but alignments are also very important for if the data does not fit the model, to basically push the data back into the model. And we compute where we are making such changes and we are generating diagnostics for that. But we have the ability that even if the data does not perfectly fit the process model, we just squeeze it into the model. And this is very important because we would like to use the data also for cases that do not completely fit, to compute bottlenecks, to do predictions and all of these things. So this is something that is very important. And after squeezing the data into the model, we can do time analysis, we can do cost analysis, and like a whole world of supervised machine learning problems is showing itself if we do that. Alignments will be covered in much more detail in, let's say, dedicated process mining courses like BPI and APM, as I also indicated at the beginning. Okay, so in detail I explained to you how you can check conformance, and that's something that you should also be able to do with pen and paper. After you have replayed reality on top of these models, a whole array of possible supervised learning problems, let's say, emerges. And I'm going to give you some examples. So just to refresh what we have seen in the first couple of lectures, what is a supervised learning problem? We have a table, we have different features, we have every row corresponds to an instance, and we have a special feature that we call the target feature. And in terms of the descriptive features, we would like to predict the target feature. So now the question that you should ask yourself, okay, we've looked at discovery, we've looked at conformance checking. How do these types of things now relate to, let's say, this framework of handling supervised learning problems? Yeah, and of course, target features can be categorical or numerical, just like the descriptive features. So if we map this onto process mining, then the instances correspond to what we call situations. So a situation can be a case as a whole. When we are, for example, interested in flow time, it could refer to a particular event. It can refer to making a decision. It can refer to executing a certain phase of the process. So we need, from the event data, using the process model, we need to create situations, rows in this table. And the features are then computations over the event data related to such a situation. So if I take the example of, for example, flow time, how long does it take to handle a case, then my situation is an entire case. So the process is executed from beginning to end. And our target feature is the flow time, which is a computation between the difference of the time of the last event minus the time of the first event. And then we have such a derived target feature. And then we should think, okay, what are now our descriptive features? And descriptive features could, for example, be how often have I executed an activity? Or which person worked on that activity? Or what was the address of the customer? And we can take all kinds of elements into this feature representation to predict the flow time of a case. And this is very general, and let's say process mining tools are exploiting this ability to generate these standard supervised learning problems. Because what you all know is that once we are at this level, that we have a table like this, we can use decision trees, we can use regression, logistic regression, neural networks, we can use the whole array of things that we have seen before. So if we look at decision mining, which is a sub-branch of process mining, then we look at decisions in the process, and we create a situation for every occasion that we need to make such a decision between B or C. And then these are then our instances, and then based on the features we can get different expressions. So for example, which cases require a thorough examination, in other words, that execute B rather than C, then there could be answers like the ones that you see on this slide. So you can identify that it was typically done by a particular person, or it was typically done by cases that were late, etc., etc. And we can do that for every decision point. So in the PetriNet, these are places with multiple output arcs. So this is another decision point, and we can again generate these situations corresponding to instances, and then, for example, find out that cases above 500 euros typically get rejected. We can of course also do the same for let's say performance. So now our target feature is not, let's say, something categorical. Do we go left or do we go right? Now we can look at, for example, numerical things like flow times, etc., etc. So which cases took more than 2 months? and we can get diagnostics indicating what cases that took more than 2 months have in common. If there is a point where there is a particular delay, we can also generate diagnostics, possibly explaining what the root cause is of such a delay. Of course, as always, you should not mix up correlation and causality, but in the data there is a lot of information to help you to diagnose such problems. If you look at compliance, then in our data we see that activities are being skipped, and we can also distinguish between the cases which skipped a mandatory activity and the cases that did not skip a mandatory activity. And again, we have a supervised learning problem. And we may find out, let's say, for example, that certain people, certain customers, certain temporal properties are causing this problem. The same with respect to if there is if we have a deviation where both pay and reject are being executed, you can again look at the cases, what they have in common when this is happening. You can do this offline, but you can also do this in an online setting where you're already, so you've learned your process mining models, you have created your predictive models based on this, and then you can make statements for running cases. And so here I have, for one case, let's call it the red case and the blue case, I'm indicating their states, and using, let's say, these supervised learning problems generated on top of process mining results, we can answer questions like what is the expected remaining flow time of a particular instance, and like that should be clear what it is. We can predict what is the remaining time. We can also predict what is the outcome. So here we could, for example, see that cases that are following a particular order in the beginning of the process have a higher likelihood of being rejected at the end. And because we have this information, we can, for running cases that are in the middle of the process, we can predict whether, let's say, something good or something bad will happen. So the general pattern, and because this very nicely connects to, let's say, things that we have seen in previous weeks, is that we can take event data, we can take process models, then based on this we can do feature extraction. Then when doing the feature extraction, every row corresponds to what we have called a situation. So a situation can be a decision, it can be a case as a whole, etc. Then for every situation we have a target feature and descriptive features, and we simply generate a supervised learning problem. And this pipeline is super general. We can apply this to performance problems, we can apply this to compliance problems. It's super generic. So this is linking back to the point that I've made also in previous lectures, and I think the last part very nicely illustrated this, that we can combine these different data science techniques. And so we can do pre-processing, then we can get a discovered process model that is, for example, showing the normal mainstream behavior. Then we do conformance checking and we find out, okay, what are the cases that are now deviating. Then we can create such a situation table indicating, for example, for a particular compliance problem, and the target variable is, okay, does this compliance problem occur in this case or not? And then based on such a table we can automatically construct decision trees that are explaining what do these deviations have in common. I think this should be clear. I'm showing this often because it's very important in this course to not look at all the techniques in isolation, but to see that they build on each other in various ways. There are like Lego bricks that you can put together to make very sophisticated data science analysis. There's another pipeline where we do first pre-processing, clustering, and then process discovery. And so this is a typical pipeline that you use if you first apply process discovery and the model seems to have structure, but the model is way too complicated because there are different process variants where things somehow seem to have a pattern, but these patterns are kind of disagreeing. So what you can then do is you can apply clustering first to your event data, and then you find, let's say, you partition the set of cases into different groups. Then you do process discovery, and you can find very simple groups or very simple process models for each of these groups. So at the very end of this lecture, I would also like to say something about tooling and the ecosystem. What I will also do is that I give you a demo of let's say, a commercial process mining system so that you have a better idea of the capabilities that they offer. So tooling, this is a slide that I also showed in the previous lecture. So there are over 35 commercial vendors. And they are all based on IDs that have first been developed in the academic world, notably the work that we did in the context of the PROM process mining tool. In the previous lecture, I showed you already, let's say very briefly, PROM. You will also use PROM if you're, for example, taking the BPI course. So PROM is an example of an open source tool, but there are more tools, and in this course, because we want to unify things, we are using PM4Py, and PM4Py is a Python library able to do the basic process mining tasks. These are, let's say, some logos of the vendors that are there, just to give you an overview of things. Some of these vendors are very large and incredibly successful. Some of these other vendors are, let's say, small or very specialized, focusing on a specific platform, like, for example, ClickView or Power BI or any of these other existing platforms that exist there. This shows you Disco. Also showed an earlier thing. I just showed these slides to give some impression. So this is process discovery and the exploration, and in Disco you can, it's super easy to use. It's much simpler than using an Excel spreadsheet, and you immediately have results. And there is this, for example, this whole environment to very intuitively filter and use your data. This is very much very useful when you get a new data set and you want to explore it. It is less useful for people that have no knowledge of process mining to look at, because it's more like a data scientist tool, so very too easy to use, but people need to be able to interpret the data. So it offers also animation, so you can see moving tokens that correspond to the actual cases flowing through the process. Here are some older screenshots of Celonis. In a minute I will actually show it live. What you see here is that you can again discover processes, but here you have this dashboarding capability. So for example, I can show pie charts, bar charts, and if I click on a pie chart or a bar chart, the process model will change because it will only consider the cases corresponding to the part of the data that I selected. Also you have animations, conformance checking. What you see here are directly follows graphs, but for example they also support the inductive mining algorithm that you've learned in the previous lecture. This is a screenshot of Minute. It heavily depends on this notion of a directly follows graph. but it provides different views: performance view, frequency view. You can also look at user resources. This is another tool. You can see that on the one hand they all are different, but somehow have very many commonalities, showing frequencies, bottlenecks, etc., etc. So some of them also provide possibilities to do comparative process mining, where, for example, you have the data from January and you have the data from February. You would like to compare them. Okay, as I mentioned before, in the previous lecture I briefly showed you some things of PROM. In your assignment you are using PM4Py, because we stick to this Python ecosystem in this course. However, I also want to give you a bit of an impression of what one can do in the context of commercial tools. And I'm now going to show you, let's say very briefly, how things look like in the Celonis process mining software. Here I opened Celonis. I create a new project to demo, let's say, a simple application using SAP data. I can connect it to SAP, but I'm now loading a CSV file, very simple. So you can see here all the columns in the CSV file. There are various attributes related to purchase orders. Now I load the data, I check the types. For example, is the date in the right format? Now I need to select the case ID, the activity, and the timestamp, as I showed in the lecture. There are more capabilities, but I will skip these here. Now I've loaded the data and I automatically generated an analysis in Celonis. So on the opening screen of the analysis you see various statistics, things related to frequency, throughput times, bottlenecks, etc. So these are the things you see here. We can also open the Process Explorer. That's one of the key components of Celonis. So we can look, just like in PROM we have a slider where we can add activities. So by moving this up, I'm adding activities. When I'm all the way at the top, all the activities have been added. The same holds with the, let's say, infrequent connections. I start with the most frequent ones, and then I can incrementally add the connections that are less frequent. And if I move everything up, then we see what reality really looks like. It's very much spaghetti-like. You can interact with the data and you can see, let's say, typical executions, rare executions, and they provide a very powerful impression what is really going on. Here I simplified it a bit. I moved the sliders down. You can annotate the nodes and arcs in different ways. For example, I can look at the average time expressed in days or expressed in hours, or if you want, also expressed in terms of minutes. We can also look at the median time rather than the average, and then things change slightly. We distinguish between case frequency and activity frequency here. We can also do the animation, just as you have seen in PROM. And we can influence the speed of the animation. So all the red dots that you see now correspond to actual purchase orders flowing through the SAP system. And we can basically move along the timeline to see whether there are bottlenecks, for example, shifting from one part of the process to the other part of the process. So this is the basic functionality. And it is also very easy to build your own functionality. So what I do here is I create a new app. I add to the app a standard component called the Variant Explorer. I'm now still in edit mode. I just resize things a bit. And this shows us all the different variants. And when you select a variant, you basically update the model. You can, of course, change all kinds of settings from the way that these apps looks visually. That's not so important. Here we are now just looking at the most frequent variant. And if we move it down, we are now looking at the top 5 frequent variants, top 7 frequent variants, and here we look at, let's say, all the variants. And we have seen what the process model looks like if we consider everything. So here I go back to the top 3, and I have all the same capabilities. So I can look at average times, I can look at frequencies, I can do all kinds of, let's say, operations on these models. So by playing with the number of variants that you consider, you can make the model more simple or less simple and distinguish between frequent and infrequent behavior. I'm now adding 2 additional components to my app, something showing the throughput time and something showing, let's say, the where we can select the activities. So if we first focus on the window that is showing the median throughput time, this is a bar chart where on the x-axis you see times, and I can basically select time intervals as wide and as narrow as I want them to be, and depending on the time interval that I choose, the most frequent variant is changing. So I'm now looking in every of the different time periods, what was the frequent variance. And you can see that the very fast frequent variant is very different from, let's say, the slower frequent variants. And we have all the capabilities, so we are now combining throughput time together with let's say, the frequencies. And this gives a good impression of what do slow cases have in common, what may be causing what is happening. So now I may have the idea, okay, I think that price changes are a problem. So now I selected, now I made a kind of filter for these price changes, and if I do that, you can see that the throughput time goes from 15 days to 27 days. So the throughput time almost doubles if we look at the price change. And now we are, let's say, zooming in and out on the cases that have these price changes. So now we can look, okay, what kind of behaviors do these price changes have in common? And we can combine, let's say, selection of activities with selections of times and selecting, let's say, certain frequent process variants. And so everything can be combined. What you see at the top is that I'm now stacking different filters. So now I'm removing all the filters, and we are now back to the original situation that we have seen before. So whenever we select something, we also see that the views are updated. I can also, for example, select an arc. I'm looking at an arc that I don't like, for example. The connection between price change and vendor creates invoice. And now I've filtered it based on all the cases that have that particular behavior in common. And you can immediately see when I do that, that it is changing in all the different tabs. So now I'm going to add another, let's say, page where I would like to do conformance checking. So we can load the model, make it by hand. I use the inductive miner. So Celonis is incorporating the inductive miner combined with variant selection. So I'm now selecting, let's say, the top 6 variants, and based on the top 6 variants, I learn automatically a model. Let's first take a look at the model. So this is what the inductive miner has generated. So behind this BPMN model is actually a process tree that was used to learn it. So we now have, let's say, a normative process model. We could also have made that by hand. And with respect to this normative process model, we see what is different between deviating cases and non-deviating cases. And so the deviating cases on average have a much longer throughput time, from over 30, so it goes over 30 days if we look at the violating cases. And when we have selected the violation, so for example, here I'm looking at a violation that there was a price change, and in my model I do not allow for it. I can immediately see that in all the different tabs. So here you see a sorted list of violations. In text it is indicating what the violation is. Note that here token-based replay is being used. There may be many deviations that I do not consider to be harmful at all, and I can whitelist them. And if I whitelist them, they disappear from the list. And if I go to the whitelisted cases, I can also add them back, that I'm again checking them. And so we are not checking the whitelisted cases. I hope that this gave you a better idea of what these commercial, let's say, process mining software systems are offering. Okay. To conclude the lecture, I'm going to make some advertisements, also because, let's say, the topic of process mining is one of the core topics that we research in our group, and I think it's fair to say that we are world leading in this particular area. So I would like to tell a bit more. I thought that this would be a good point to explain a few things, and also to motivate you to do an assignment in this area. I just gave a brief demo of Celonis, by far not extensive, but if you look at a tool like Celonis, then you can see that there are many elements in there which basically directly come from research. So there is the directly follows graph / heuristic fuzzy miner that existed already in PROM, let's say almost 20 years ago, that were adopted by Celonis right at the beginning, when they founded the company. Some of the other things came later, so they are, for example, doing conformance checking using token-based replay. Token-based replay was invented in 2005, that this was first implemented in the context of PROM. In 2017, this was added to the Celonis system. So these green numbers, they correspond to the difference when we developed it in research until the point in time that it was embedded in Celonis as an example of a commercial system. Then was this ability to generate supervised learning problems that I talked about in the second half of the lecture. This ability to generate supervised learning problems, we already had envisioned that in 2006. Then we already had, for example, a decision miner in the context of PROM. This was added to the Celonis suite in 2017. Something more recent is that the inductive mining approach is relatively young. We started to talk about this and to show the results in 2013. In 2018, this was added to the system. Another example is the token-based animation, where you can track actual cases through the flow. That was also the difference. So this is nicely showing how things developed in academia ended up in commercial tools, and this shows a bit how these interactions work. So we develop new algorithms, apply them ourselves in all kinds of, let's say, real-life settings. We often also use synthetic data, for example, if we are trying to create certain benchmarks or to see the effect of a parameter, but we also use lots of real-world data. Also much data we have made publicly available. That leads to new challenges and new ideas, new algorithms, and we are constantly going through this cycle. Also motivating, let's say, the software industry to take these adoptions. And through the software industry, companies like UiPath, Celonis, MyInvenio, Fluxicon, QPR, etc., they are selling tools to industry where it is applied in a large scale. So for example, the software of Celonis is used, I think, in over 2,000 organizations. Organizations like Siemens, BMW, Uber, etc., etc. And in some of these organizations, like for example within Siemens, thousands of people are using this process mining software. I'm sketching you this because it helps you to see that there is lots of potential for nice, let's say, thesis projects in this space, also with the connection to, let's say, real-world applications. So if you would like to specialize in this, and as I said, as I warned you, this is a kind of advertisement. If you like this type of research, there are, let's say, of course, all kinds of thesis topics possible. I've mentioned the BPI and the APM course. These are possibilities, seminars, etc., etc. We also have, let's say, lots of possibilities for Hiwi jobs, but there I would like to ask you to not, let's say, randomly apply, only apply for a Hiwi job if you have already done some of the other things that are here. So that you have shown that you have process mining expertise in such a way that you can do something, let's say, meaningful. So if you're interested in these things, yeah, you can go to our website. There we list thesis projects. There are many more possibilities than what you see there. You also find information about the courses that we offer. So this was the end of the brief advertisement, but since the topic of the lecture today connected so well to the type of research that we are doing, I could not resist the temptation. Okay, let's come to a conclusion of this lecture. So I hope I made you enthusiastic for the topic of process mining. That's why I also added the advertisement at the end. In the two lectures we looked at both unsupervised and supervised process mining. Process discovery is clearly unsupervised, but in the lecture today I also showed that you can generate all kinds of supervised learning problems. So for example, getting explanations why there are certain deviations in the process model. Lots of opportunities to dive deeper. So we have now covered 14 lectures, and we already moved into the area where we start looking at data that has particular properties. So the last couple of lectures, including the lecture on sequence mining, we have been looking at data with a very clear temporal dimension. So events happen at certain times, and we have been exploiting these properties. In the next two lectures, we are going to do something similar, but we are not going to exploit the temporal dimension. We are going to focus on data that corresponds to text. And just like time has certain properties, also text has certain properties. For example, a document is composed of words, and a word is composed of letters. And that structure, we can exploit that when we are dealing with text mining. And that will be the topic of the next two lectures. Thank you very much.